about debugging writ large. And I'm going to be talking to you about a quite broad subject, and evidently it's going to occupy us during the balance of this lecture and the next lecture as well. There's some really good references. It took me years to discover these. They're really great. One of them, I said before, and you can see the value of God over the years for these things here, but it's called Black Program Scale, and it lays out a systematic means of sort of figuring out what's wrong with my program, pursuing it in a scientific way that can speed up by integer factors, 3 times, 4 times, maybe even more, how quickly you can come to the root of a problem. So that book is highly recommended. There's also a book called The Practice of Programming, which covers a lot of topics discussed in this course, Kernahan and Kite, and it's strongly recommended. Kernahan, being perhaps more famous, is one of the key creators of C and Unix. And then finally, there's a book by Metzger, Debugging by Thinking, which is a good tone. Okay, so I want to start by distinguishing these. Oh man, I can just feel the testability of this. This Friday may be Black Friday for shopping, but I don't typically partake of that in a heavy fashion. But I will be. It may be Black Friday, sort of in the sense that it's time to start. It's time to start putting my real effort into creating more problems for the final. Fortunately, you get a review session before that. 2 review sessions. Okay, so faults and failures. So, ladies and gentlemen, one of the reasons software is so challenging to work with is because we're working with intangible software. We're working with concepts, ideas about how something should work, and we can't, point to something and manipulate it in a sort of very tangible fashion. And often that means communicating to people about what we're doing, what we have done, how we're going to change it, what our plans are. It's more challenging. We can't get a clay mock-up that we can show to anyone from whatever walk of life to say, this is the building we're going to build. Instead, we can diagram out an architecture, design using UML, or using any number of sort of types of diagrams, data flow diagrams, swiveling diagrams, what have you. And that's a language that's not familiar to, it's a vernacular that's limited to computer science. And one of the challenges in getting programs working is that often the underlying problems are just not evident from the evidence we have. So when we run a program, there may be an obvious failure that occurs. It fails to conform with the requirements which we've laid out for that program. This needs to compute the total across these population statistics of the income or the mean income. It may be that we want this program to display a map of this certain area of the world with these things juxtaposed on it. It may be that we want this program to do something simple conceptually, like print out the end time number. And there may be failures which are clear departures of this program from its requirements. So the most obvious case is a crash. We're running it and it dies in front of us. Another case is it halts or hangs. Maybe it doesn't run in the first place. I'm sorry, when I say halts or hangs, what I mean is it just stops processing. It's there, it's sitting in front of us, but it's not responsive, right? It's hanging and we can't get it to do anything. In other cases, it doesn't run in the first place. Another thing is it shows incorrect results. It shows us the wrong area of the map, the wrong area of the world. It puts the items on top of that map in the wrong places. Maybe it behaves in an inconsistent manner. Sometimes when we run it, it does one thing, sometimes another. Maybe reporting values that are implausible. identifying that is often far harder than finding the failure. Finding the failure may be a matter of running test cases using an automated software system and looking for premature program halts, looking for example, output that's incomplete or corrupted, etc. In many cases, we may be able to get by on that. Finding faults, ladies and gentlemen, is traditionally a singularly human activity. It's something that we have to smooth out. It's something where we play Sherlock Holmes, as it were, to try to track down where is this problem coming from. What's the core underlying problem that led to this failure? Sometimes it's more than one defect, underlying defect, that leads to this failure. But we're going to speak of it as the fault, because that's the most common case. There's a single sort of mistake somewhere in our program. Okay? Now, the problem is compounded by the fact that, well, often our program will hang, or it will crash, disappear off our screen. It may not be obvious exactly where it comes in the program or exactly where it crashed. Finding that takes some effort. But even if you find that location, you say, oh, here's where it gets hung up. It gets hung up on this call to open the database connection. Or this is the place where it just dies suddenly. It never gets beyond this point, and it gets to this point, but never beyond. Great. We found the location of the failure. Have we found the location of the fault? No. The fault could be close by. Could be that we just didn't check the case, whether the pointer is null. And we read star p equal whatever. And if we had only checked it, we would have realized, oh, we should just return null instead of writing. Could be that simple. Could be very proximate, or it could be very, very distant. Okay. So it may be that somewhere up in your code, long before the failure, there's an algorithm which assigns elements of some array. This is an array of pointers, and maybe when your program is just starting up, it goes through each element of the array and creates a pointer for that element. It allocates some memory and puts it into that element of the array. So this is an array that contains pointers and goes through each and every one, but it forgets the last one. It doesn't initialize the last one. The last one is null, and it doesn't initialize. So you have an off by one error. Go up. Do it one less than we need to. Okay. Later, much later, minutes later, days later, even sometimes, we may use that element of the array. That last element, which was supposed to be initialized. And we try to dereference it. We try to do star p equals whatever. We take it out of the array, that p, we plug it out of the array, we try to do star p, and it blows up in our face. Where is the fault here, ladies and gentlemen? Is the fault in the star p equals whatever? No, that's not the underlying fault. That would have been fine if only that code earlier had been written properly. The programmer's intention was to fill up each element of this array, but they were off by one. They neglected the last element. And had that been done per their intention, it would have all worked. This is the underlying fault. So, when we consider faults and failures, we have to realize that there's often a quite articulated sort of process that leads from a situation where the program was in some sort of, we call it sane. It had a sane state. Everything was solid and per design, per plan. And then at some point there was some erroneous code. Maybe it was this faulty algorithm. Maybe it was, we initialized this variable with an empty number, and we never, for a certain path of execution, we never initialize it with a proper value. Maybe we just use this uninitialized value given by default. And that leads to an infected state, what we call an infected state. A situation that's not per our intention. Wasn't what was intended. Certainly wasn't what was needed. And that infected state might propagate through our program, start affecting a lot of different things, until it finally leads to an observed failure. Maybe this is the crack. Maybe this is the instance of data corruption that is noted. Maybe this is the situation where it hangs. Now, what we're trying to do, ladies and gentlemen, in debugging is find this error or code. And that may involve backing up until we find the real source of this, the heart of the matter. And we want to be very cautious about just plastering over this failure, just hiding it, hiding the underlying defect by eliminating the failure without eliminating the underlying fault. So here, I've just sort of given a little narrative here for one particular case. So, here we may have had this array we created. We filled it with nulls. Great. All the values are initialized to null. And then there's some algorithm that goes through and fills all of them except the last. It overlooks the last. It fills them all up with good references to things in the heap. Good references to things that allocated with count or malloc or new int brackets, etc. Right? And initializes all of those. And then later on, there's, this array is still continuing on. And maybe after a certain point, the last element of the array is obtained. It's assigned to a local variable. P equals this array, call it array of I. Grabs that null value out of there into P. And then later it goes star P equals whatever. And that's where things go sideways. That's where things go haywire. But that's not the underlying problem. This is the sign of the problem. It's a symptom of the problem. The cause of the problem, ladies and gentlemen, was way up there. And it may have, again, occurred hours or even days earlier. People appreciate that. Okay, so there's a series of terminology that's been built up around different sorts of bugs. In most cases, we deal with what are called Gore bugs. These are bugs that are repeatable. It's going to repeat under a very well-defined set of conditions. We may not know what those set of conditions are, but the thought here is that the conviction here is if we put our effort into these, into localizing these conditions, we can come up with some set of conditions that repeatedly causes the failure to occur. It repeatedly causes this failure to manifest. And that, ladies and gentlemen, is the first step in getting us towards being able to debug it effectively. Getting that failure to reliably repeat, and hopefully doing so in as simple a fashion as possible. There are some cases where we get Heisenbergs. And ladies and gentlemen, if I were to put up there on sort of high-level programming, so-called high-level programming languages, if I were to graph out for different high-level programming languages the frequency of Heisenbergs for Java, for C#, for Erlang, for Python, for Perl, for all these different languages, and I were to put C on there, C would stand hand and shoulders above the other. But I will say this: of C bugs, so I spent a huge amount of time debugging C bugs. It's maybe 1%, no, less than 1%. Maybe it's 0.5% of C bugs that are Heisenbergs. I mean, it's not like every bug is a Heisenberg. By no means. It's just they do occur, and the reason they occur big time is because of memory allocation. Because you change how the memory is laid out, and it changes how the memory allocation occurs. So if you have the debugger loaded with the program, it now has different memory access, and so the bug will disappear for a while. Is it there? Is the fault there? Yes, the fault is there. Just because the failure doesn't occur does not mean you're safe. The fault is there. Okay, so I provided, and I'm going to post all these slides, but I provided some common types of bugs. I'm not going to go into them in detail so we can go into the debugging process next time, but I will put these up for you to take a look at. Then we're going to be talking about scientific debugging. We can actually go about system